It's really a pleasure to have Massimo back. He'll be telling us about local operator algebras in gauge theory and gravity. We'll be taking Massimo out to dinner. Is like sorry, I forget. As a fancy person, you like dinner later or earlier?
Early.
Early. Okay, great. So let's gather in Bloomberg around 6. Is that reasonably early? Okay, let's gather in. Oh, and whoever wants to go, just send me. And take it away, Massimo.
Thank you, Nima, for this invitation. Always a pleasure to be back here. Today, I'll talk about a proposal for a better, what I think is a better construction of gauge invariant states in gauge theory and gravity, a construction that preserves some notion of locality. So here is the plan. I will just remind you of the local charge of the problem with local charged operators and gauge invariance. I will give you an example of how gauge invariant operators are constructed, starting with the simplest case, QED in Minkowski space. I will say why I think that this is not ideal and propose a possible improvement done by trying to even operator dressing to states that are initially not gauge invariant. And I will, of course, tell you what all these things mean. To do that, we need to introduce the BRS charges and do everything in the language of BRS cohomology. And in particular, I will do a perturbative construction, no claims of being non-perturbative. So it will be something that is order by order, some parameter that could be the coupling constant, could be something else. And to do that, I need to split the BRS charge into a free quadratic part and the rest. Define a anti-BRS charge, but only for the free part, and also some counting operator that gives a filtration for the charge, for the real total BRS charge. I'll generalize my construction to Yang-Mills and gravity and show how actually to construct the operator dressing, in particular technically how to construct an intertwiner between two cohomologies, a simple one and the complete physical BRS cohomology. I will spend some words talking about closed Cauchy surfaces and changes in the construction that are needed when surfaces are closed. Relate my construction to other construction of gauge invariant states that exist in the literature, and then talk about states. So let me start with the simplest example. QED, Minkowski space, I work in a Hamiltonian formalism. So I work on a fixed Cauchy surface at time equal to 0. And here I illustrated so that this is the surface. Now, I will ignore all the famous subtleties related to the fact that when you talk about operators in quantum field theory, you should really smear a little bit in time. So my construction will be formal from this point of view. Now, in QED, as you know, a charged local field is not physical because it does not commute with the Gauss law constraint. And the simplest example is, say, you're in electrodynamics and you have the electron operator psi, right? Well, this object does not commute with the Gauss law, so it's not physical. How do you make it physical? Well, we can do like Dirac did. Dirac, long before Wilson lines, etc., worked in a canonical formalism. And so in a canonical formalism, the vector potential and the electric field are canonically conjugate variables. They have the standard commutation relations. And if you use these fields, and you can construct a dressed field that has this form, and this form is very suggestive. You see that you have the vector potential multiplied by the classical electric field created by a source located exactly at x, at the position of the local operator. Now, this dressed operator is physical, but it's not local because we have multiplied by the subject, and you see that here we integrate over all the equal to zero slice or the Cauchy surface. So now the fact that we need non-local fields is unavoidable because we can see, for instance, that if we look at the integrated version of the Gauss constraint, right, we have Gauss law integrated over all space-time. This can be converted, this first term can be converted to an integral over a surface at infinity that commutes with any local fields. Right? Remember, we are at the same time on a Cauchy surface, while the second term commutes to the charge. Right? So we get something that is non-zero. And as long as we have local fields, we'll always get a non-zero result when we commute the integrated Gauss constraint. So, well, we have to give up something. Now, and so we may not care. For instance, we can say, yes, let's use Dirac's dressing, or let's use the Wilson line dressing. Again, it is non-local, even the Wilson line dressing, because we have a Wilson line that begins at the position of the psi field, and it goes to infinity. So far, so good. Now, the problem of these dressings is that they can be done case by case for each local operator, right? I mean, after a while, we know what to do, but you have to dress every single operator. Neither of the two, neither the Dirac nor the Wilson, really respect the structure of the local operator algebra. We have an algebra, some properties in which some operators commute and some don't. What happens when we dress them? We don't know. So there is no sense in which the physical fields remain local under the dressing. And we may worry that because of this, many of the results that we derive in operator algebra are not longer obviously applicable. We have many, when we have a local operator algebra, it obeys certain properties. We can use locality to prove theorems. For instance, the fact that the vacuum in quantum field theory is cyclic and separating for in algebra of local operators in a domain of space-time that is not the entire space-time. And that's based, the proof is based strictly on Lorentz invariance and locality. So if we lose that, what will happen to our theorems and the structure of the algebra? There is also another way in which we would like to have some notion of locality. For instance, when we define an island on our Cauchy surface. So for me, an island here is just a bounded subregion of the Cauchy surface. And because if we take an operator inside the island over here, right, and we dress it, well, we dress it, for instance, with a Wilson line. The Wilson line has to go all the way to infinity. And now, since there is this very long tail, you may have some, and you do have some local operators that no longer commute with the dressed operator O, right? Because it will, when you move O prime around and you commute, you may intercept this tail. So then it is not clear how to define what fields are in and what are out, at least in the standard sense in which you have two independent operators should commute if they are defined on space, mutually space-like domains. So, of course, we work with a QED for simplicity, but when we try to dress operators in other theories, especially in perturbative gravity, the stressing constructions become very complicated very soon. The Wilson line dressing becomes cumbersome, in fact, after the first order in the Newton constant. And I don't think that is known after the first few orders, because it really becomes obvious. I mean, it can be done, everything can be done, but maybe we should not do it. And so, but maybe we should think about a better way of dressing of local operators. And in particular, it would be much better if we had an operatorial dressing. So if we have an operator omega, right, yet to be defined, and if we could conjugate operators O let's say, local operators that I have to define in which sense how to define them and what is the subalgebra of these operators. If we could conjugate them by a unitary operator to some operator O hat, then many of the properties of the of our theory are preserved. In particular, if we take two undressed fields O1 and O2 and we dress them, like the product, we can first dress the product, or first dress the operators and take the product, and we get the same result. That's this operation commutes, and that's useful in defining some notion of locality even for the dress fields. Now, this omega, if it's omega is a unitary operator, that's great, but in reality, we could also define this procedure by, say, taking an operator omega defined on a finite volume, sending the volume to infinity, and defining an automorphism, even though omega is only formally unitary and is not well defined in single Hilbert space. Which is what I'm saying here. So you can have a finite volume regularization, maybe even ultraviolet regularization, define this omega, and then first compute the conjugate operator, then take the limit. That will still define an automorphism. Now, as I said before, that was already evident from what I said before, but let me repeat it. If we take a physical operator defined at some point OX, so if this O hat X is defined as the dressing of a local operator OX, right? Now, if two O commute, for instance, because they are defined on mutually space-like points, then even the dressed operator. So in some sense, we have at least a label, a local label for the dressed fields.
Omega is not local operator.
The dressed operators will not be local. And we see it explicitly. They, in fact, for QED, they will be the dressed fields. But you could still define which commute and which do not. And there is a one-to-one correspondence between local fields, undressed local fields, and dressed local fields. If the undressed fields commute, the dressed one also commute. So there is a notion of mutual locality, at least at the level of the labels in this algebra. So in fact, because of this, it makes sense to...
Is the Dirac operator what you'd have gotten in like Coulomb gauge?
In the Coulomb gauge, yes.
So the Dirac operator are just direct. So I fix my spatial surface, Coulomb gauge, and the operators in Coulomb gauge farther.
As we see, actually, it's better not to do Coulomb gauge, but to use
versus the Wilson lines, which are like temporal gauges.
Yeah. So now, as I said before, the dressed operator inherit the same locality properties of their undressed relatives. So it makes sense, for instance, to define the algebra of physical operators inside an island as by taking the undressed operators inside the island and dressing them, and create that those are the operators inside. And likewise for the states that are outside the island, that will preserve the mutual commutation of the two algebras. Now, of course, I have to construct this operator omega and show that even at least formally it exists. To do that, actually, it's better to work in the BRS language and define a BRS or BRST homology. So, which I will do later on. For now, let's say that what I'm looking for is the following. First, I want to define what are physical states, and now in a BRS homology, these are states that are closed under the BRS operators, but are not modulo the exact operators. And now, actually, the key point would be to break the BRS charge into some free quadratic part in Gaussian matter and the rest of the interactions. Because now now I can define two homologies, the Q0 homology, that would be simpler, right? And the exact homology. And so in the Q0 that I will define will actually we have a large cohomology among local operators. So there will be no problem in finding local operators that are in the cohomology of Q0, but they are not in the complete cohomology. So the way to relate it to, again, is through this operator omega. And the key property that I want from this omega is that it intertwines between the simple free quadratic homology and the exact one. So that it obeys this property, Q0 omega equals omega QB.
Why do you require that?
Well, you'll see in a moment. So remember, Q0 is a simple cohomology that I know how to solve among so I can take local operators and I can find a non-zero cohomology. And then, well, what I want, of course, is QB. And if omega obeys this property, then I will be able to construct the exact cohomology in terms of the free one. Now, but first of all, before constructing omega, I have to construct Q0 and QB in a convenient way for my purposes. So in particular, I need I need to find the cohomology in a canonical formalism after gauge fixing. And so let's proceed to do this first for QED. So I want to construct the exact QB and then split it into the free part and the rest in terms of the canonical coordinates and the momenta of gauge fixed QED. So I am resolutely perturbative, so I want to write something that makes sense in perturbation theory. In perturbation theory for this theory around the free Maxwell theory and matter. So it's when you work in perturbation theory, it's very convenient to use a covariant formalism, a covariant gauge fixing, not a Coulomb or a temporal gauge fixing. And you can do this a la Nakanishi-Lautrup by writing the Lagrangian of, say, Maxwell field, matter, and then this gauge fixing Lagrangian, where if you integrate out rho, you'll get all the psi gauges that you want. And this is the usual BC-DOS term. Now, the action is invariant under this universal BRST transformation. Since rho is kept, since I don't integrate rho, this is really universal and works for any psi. And now, one thing that I've never seen before, it seems trivial, but I never saw it, is that actually, if you don't integrate out rho, right, rho is canonically conjugate to A0. And then you have canonically conjugate pairs of B dot C and C dot B, and that's because the Lagrangian contains B dot C dot plus terms without time derivative. So the conjugate momentum of C is B dot, the conjugate momentum of B is C dot. And again, this is the thing that I never saw before, the canonically conjugate momentum to A0 is rho. So now don't integrate rho out and you have your beautiful canonical coordinates ready for you. Which means that now you can write the RS charge in the canonical formalism as operators acting. Vector space. So, and the BRS charge here, I mean, the splitting is quite obvious. I can just take this quadratic part at a charge equal to 0 plus the coupling to matter. So this is what generates the linear transformations on the field. So it's what transforms the longitudinal part of the gauge potential, right, and the ghost. Now, well, now the next thing that we need for our construction, so far you may say, why? Well, we have to construct this thing is to construct a conjugate operator, but a conjugate operator that only has to have some nice commutation relations with Q0. The nice commutation relations are the following. this conjugate operator, this anti-BRS charge R, anti-commutes to something that's proportional to another charge, which is actually a counting operator under which the free part of the BRS charge is neutral, while the other has positive charge, here charge 1. And so the way to construct this is essentially by trial and error. That's easy to do because we only want an object R that has simple commutation relations with Q0. And Q0 is a very simple object, it's quadratic. So here is the answer. It's just, well, this object has BRS charge 1 because there is this C that is it goes at this charge +1 under the usual BC charge, right? So we want something that has charge -1. So we want something with the B ghost. You can have a term in B and a term in B dot. And well, with a little bit of trial and error, you arrive at this form where beta is simply the Green's function for the Laplace operator on our flat Cauchy slice. Now, the choice of R is has to give us a charge operator. And in fact, now if beta is the Green's function of the Laplace operator, we'll get this nice formula, Q0 anti-commuted with R. I write it as I times an anti-Hermitian charge. This anti-commutator is Hermitian, so I write it as I times an anti-Hermitian charge. And this anti-Hermitian charge does what we want, counts the BC ghost and also the gauge variant components of our electromagnetic field. So the longitudinal part of the gauge field in this zero.
Sorry, what's pi of x and pi of x? The last terms and
let's see, I have
last terms, capital pi and capital pi.
Oh, yes, I should have defined phi. Phi is this integral over here. And so it's a non-local field defined by applying the Green's function to this to the divergence of the vector potential, and pi is the conjugate momentum to A. By writing explicitly these terms, I could also write this object in terms of the divergence of A and the divergence of E.
Wait, phi is a scalar, pi is the conjugate momentum to what?
To phi.
Oh, to phi.
To phi, yes. So phi is this integral. So. Now, in fact, here I wrote it maybe in a more explicit way. Now, there are no localities everywhere, right? Because there is a Green's function here, there is a Green's function hidden in the definition of phi, which is this, right? But this is a harmless no locality because here beta is the Green's function for an elliptic operator, right? So it does not introduce on Chanel poles, which would be present if I was.
Are you working in the
Green's
Euclidean
function.
signature?
Sorry?
Are you working in Euclidean signature?
I'm working at t equal to 0 on a Cauchy surface. So this is a three-dimensional, everything here is three-dimensional. So here I'm not introducing dangerous non-localities because I'm not introducing a Green's function of a hyperbolic operator. And the nice thing of S is that it's a counting operator. It counts each ghost C and C dot with a +1, each ghost B dot and B with a -1. Now the gauge, the longitudinal components of the potential, so the time component and the gradient of A are counted with a +1, and instead the conjugate momenta, which are rho, and the divergence of the electric field with a -1. All the rest is neutral. This operation. So this is a counting, it's not a ghost number counting, it's just accounting for the longitudinal part of your fields. You may remember something similar in Polchinski's proof of the no-Gauss theorem in the bosonic string, where he also has a simplified BRS cohomology, and then he has told that the cohomology is isomorphic to the cohomology of the true BRS operator. In doing that, he also defines a counting operator that only counts the longitudinal modes, and under which the transverse. So here, in a sense, we followed that hint, and we define something similar in QED. Now, let me look at some generalization, and then I'll tell you what to do with this operator, which I didn't. So the generalizations are actually, well, one would be, the simplest one is to take QED, but on a generic Cauchy surface, so under which my Minkowski space is some interval or line times some 3D space-like surface. The difference is that instead of having some explicit contraction, I have some Hodge duals, and some forms, but for the rest, the structure is really the same. So I have a quadratic part for Q, an interacting part, in the case of QED, this is still cubic, and then again, the R operator, it's only constructed using Q0. So it doesn't matter how complicated is Q1. We only need to anti-commute to Q0 and get an expression for the counting operator for this charge. Now, again, the surface is open here, but for the rest is generic. And beta, okay, not surprisingly, is the Green's function for the covariant Laplace operator. So this is an easy generalization. Now, QED is relatively easy. So in a sense, what we are more concerned with is other cases where the direct construction of an operatorial dressing or even a Dirac type dressing becomes really cumbersome.
Again, the relation between this as the Dirac dress.
I will actually, well, I can tell you it's, if you apply, well, you'll have to construct the operator omega first, and then I'll tell you the relation.
Okay.
I mean, it's not so much a punch, it's not a big punchline. Anyway, I'll keep it for later. So in non-abelian gauge theory, again, the total BRS charge can be written in terms of a quadratic term and some interaction term, charge 1. And now, again, the quadratic part, and that's the beauty, is exactly the same as for the abelian case. You have just to sprinkle some adjoint indices, but the structure of the quadratic part of Q is exactly the same. Hence, the structure of R is exactly the same, except for the fact that now you have to sum over all the adjoint indices. Nothing changes. Q1, the interacting part is more complicated because now you see terms that involve the longitudinal components of the electric field and the gauge potential, transverse parts, and also these cubic terms involving ghosts. Phi is defined as before, is this non-local field obtained by taking the divergence of the vector potential and multiplying by the Green's function. And this beta should be an S, sorry, this is a mistake. S, as before, is this object obtained by anti-commuting Q1 and R, and this accounting operator. Now, this counting operator, again, since it's only constructed involving the quadratic part, will be exactly the same as in the abelian case. So it will count some fields, in particular the longitudinal electric field, rho, which is the conjugate momentum to A0, and the anti-Gauss BNP dot with charge -1, the longitudinal component of the vector potential A0, and the C Gauss instead with charge +1, or the rest at charge 0. And again, here the important thing is that S is a counting operator, and that the exact charge decomposes into a quadratic piece of charge 0 and an interacting piece of charge 1. Now, here I just sketch perturbative gravity, which is a bit long here. But the key point, so here, if I construct perturbative gravity around the Minkowski background, in order to do I want the canonical formalism. A canonical formalism also in the presence of a covariant gauge fixing, which is here it will be the usual harmonic or the Dondel gauge fixing. This d bar, well, is simply the covariant derivative around Minkowski background, so that's just the ordinary derivative. The gauge fixing part is this. So you see that the important point is that now there will be the rho mu, which has a vector part and has a time component that I call rho simply, will be canonically conjugate to what before were just constraints with the lapse and shift, with the component G00 and G05. So here I have exactly the same structure as in electrodynamics. Now I have a bunch, all coordinates are good canonical coordinates. Each coordinate has a momentum. So the B ghost has a conjugate momentum that I call pi of B, that will be C dot, right? The same thing for the vector ghost, anti-ghosts. The vector ghost will have a conjugate momentum that is Pi dot. The C0, which I call simply C, so the time component of the ghost has its own canonically conjugate. So all of these are essentially standard in any gauge fixing. I would say that the new thing, maybe the new simplification, is that if you don't integrate the Nakanishi Lautrop field exactly as in the case of gauge theories, you also have universally defined conjugate momenta for the lapse and shift.
And your definition of delta of beta ik, I mean, do you really mean derivatives or covariant derivatives?
Oh, here I am expanding around the Minkowski background, so these are just standard derivatives. When I expand around other backgrounds, we have to use covariant derivatives, and
With respect to that, then.
with respect to the background metric. And in our paper, we only, we did Minkowski, and we explained how to construct these charges in the case of maximally symmetric backgrounds. We couldn't do a construction for a generic Cauchy surface in an arbitrary metric, which is one of the things that we are trying to do right now. So far, our construction was for Minkowski, de Sitter, and de Sitter. But we definitely want to do the construction in particular, for instance, at least the eternal Schwarzschild black hole. And because there we could connect what we do here to what has been done in papers on, say, cross product on algebras, etc. So here we are just in Minkowski background, and again we define. Now, maybe the only difference with respect to the usual gauge field story is that this field phi, instead of being a function of the fields of the metric, is a function of the extrinsic curvature, well, of the conjugate, the canonically conjugate momentum to the curvature, to the trace, actually. For the rest, the structure of our operators is rather similar to what we had before. So we have a quadratic charge that for gravity is relatively simple, a conjugate operator and a counting operator, and that has this form. Again, pi b is the canonically conjugate momentum to B, right, and pi c. So we have this expression, and now, when we write the BRS charge, it is slightly more complicated than before, but it still has a similar structure to what we had earlier. So the complete charge is a term with charge 0 under S, and a bunch of terms with positive charge. Now, the important part here is that all these Qn have positive S charge. It doesn't even matter whether they are finite in number. And in fact, this is the key property that we need for our BRS charge. It holds also for perturbative gravity in arbitrarily maximally symmetric backgrounds. And it's thanks to this property that now I can construct the intertwiner. So far, I just defined a bunch of objects, but I have to tell you why I did that, right? And how to construct the intertwiner. So this is really the key property. This sum is for n positive. So here is the construction, finally. Now, we have a charge, a BRS charge that decomposes into a simple part and a sum of terms. Here I truncated them and finite, but strictly speaking, that's not necessary. And the fact that Q has charge n means that S commuted with Qn is n times Qn. Now you see that Q is Hermitian, so S has to be anti-Hermitian. And now we define some auxiliary quantities. I define a Qt, which is simply the QB charge, but now where each term of charge n has been multiplied by e to the minus nt. This is some parameter. Right? So now, because when because QB is nilpotent, right? When I do the commutator, the anti-commutator of two QBs, I get a bunch of anti-commutators that mean, for instance, that Q0 square is equal to 0, Q0 Q1 plus Q1 Q0 is equal to 0, etc., etc. All of them imply that actually Q for any value of the parameter T is equal to 0. So I have also this property. If I decompose this Q, depending on the parameter T, into this free part, constant part, and the rest, I have that Q0 Qi plus Qi Q0 plus Qi square equal to 0. Okay. Now, using the only...
Is this because all the anti-commutators have to vanish independently in all the sectors with fixed S charge?
With these X charges. So you see that now using this property, actually I can take the anti-BRS charge, this interacting part, Qi, depending on T, anti-commute it, and then this is a bosonic operator, commute it with the complete charge, Q, and thanks to this property, I can reshuffle this commutator into Qi anti-commuted with Q0R. But the anti-commutator of Q0R is proportional to the counting charge S, and S commuted with Qi is equal to this quantity, which is also I times the time derivative of Qi, which is also the time derivative, the parameter T derivative of Qi, which is also the derivative with respect to the complete Q. And again, as you see, only very few properties of Q are necessary to arrive to this result. Now, we do the usual trick. Now we can say, this thing looks like a Hamiltonian. So let's define an evolution operator by the usual equation that you have in perturbation theory, when you do time-dependent perturbation theory, where you split the Hamiltonian into free and interactive. You define an operator omega such that the time derivative is I times Q, I times omega times this object. So I times this anti-commutator is the charge S, which is anti-Hermitian. Right? Okay, so this is all formal, so let's continue. And we define this operator now. And now, because of the identity that we derived before, now we can take the derivative of all these objects.
So the commutator is a charge S, what's like Q0R?
This is, you mean this one?
Yeah.
This is the commutator of R with this charge Qi that was defined in this way. So this is the definition of Qi. It doesn't have a definite S charge. Right?
Yeah, so you said something I didn't understand, so this commuted is multiplied by I is just a charge.
Oh, so, no, sorry, this was wrong. It's simply, it's actually much simpler than that. Qi, it's also Hermitian, Qi of t, right? You don't need to think about this. Then Qit R anti-commuted is a Hermitian operator, which means that this object is anti-Hermitian. So when we solve these equations, we'll get a formally unitary operator. Okay. As unitary as the evolution operator in perturbation theory. Now we define, again, when we define this, the evolution operator by this equation, right, then, and we can take the derivative of omega q omega minus 1, all functions of t, and now there are three pieces, right? There are this derivative hitting here, and hitting in the middle, and when the derivative sitting here and here reconstruct this object, the derivative hitting in the middle gives me q dt, but because of the identity that I wrote before, this term in parentheses is equal to 0. So this, the object that I write here is actually independent of the parameter t. Now, if I integrate this equation between 0 and infinity, and I have to give an initial condition for my omega and my charges. Well, Q at plus infinity is the free charge. Remember that all the interaction term had strictly positive S charge. And each term was multiplied by e to the minus nt. So at infinity, this is the free charge. At 0, it's the complete true BRS charge. As initial condition, I can have an initial condition at plus infinity, right? And then integrate back. So I find that Q at plus infinity minus this omega 0, Q omega minus 1, right? Which is also the free charge, free BRS charge minus omega 0 QB, the complete BRS charge, omega minus 1 is equal to 0. So indeed, this omega 0 is the intertwiner. And because this is an overkill, because this anti-commutator is Hermitian, and I times the anti-commutator is anti-Hermitian, this omega is a unitary operator. Okay. And everything here is done at the same level of rigor as time-dependent perturbation theory in quantum mechanics. So here we have our construction, and now it's useful because it defines an isomorphism between the cohomologies of Q0 and QB. Right? So in particular, if so here you see that the key point is that QB indeed is an intertwiner. So when QB passes through omega dagger, it becomes Q0. When Q0 passes through omega, it becomes QB. So here, this QB, commuted or anti-commuted, depending on the statistics of O. When, let's say that it commutes, when QB commutes with the Drest operator, then what we have is that the commutator of the Drest operator with Q is the same as the conjugation of the commutator of the free BRS charge with the undressed operator O. So in particular, if an operator O is closed under the free BRS cohomology, then the Drest operator is closed under the complete cohomology. If an operator X is exact in the Q0 cohomology, so if it can be written as the commutator or anti-commutator of some other operator O in the cohomology, then the Drest operator omega dagger X omega is also exact under the complete cohomology. So you have an arrow that goes in one direction, right? Cohomology of Q0 gives you, you have an element of the cohomology of Q0 gives you an element of the cohomology of Q, and you can reverse this argument because omega is unitary. So you get an isomorphism between the two cohomologies. And that's the key property of this story, right? So now we have a way of constructing a homology using a simple operator. And remember, under this Q0, there are tons of local fields. In fact, the homology is very simple. The homology is the homology of free abelian theories. And so any matter field is in the homology. Any charged field in QED is in the homology. The electric field, the magnetic field, right? All the transverse fields are in the homology, and products of those fields are also in the homology. So you have this big, easy to find homology for Q0, and you can apply the intertwiner to find the exact homology, and vice versa. Now, contrary to the Wilson line approach, we do not need to know the explicit form of QB. That's the other advantage of this dressing. We need to know its quadratic part, and also that interact in terms of positive S charge. So the computation involved in this construction is much less, especially when you go to gravity, right? You have just to find and play with the free Q0, find a free anti-BRS charge, and then show that don't have unwanted terms, so that the interacting part doesn't have pieces with both positive and negative charge, or with zero charge. So once you do, and that's much simpler than actually trying to explicitly construct, say, a gravitational Wilson line, even in a Minkowski background. Now, as I said before, the construction of omega requires that the complete BRS charge is nilpotent. So, in a sense, luckily, it does not apply where it shouldn't. It does not apply to anomalous gauge theories. That's a sanity check. Okay, so that was the key point, right? So for me, the two big advantages of this construction are A, that the properties of the algebra are preserved, that this construction defines an isomorphism in between a BRS homology that I know how to compute and the rest, and that we don't actually need to construct the operator omega explicitly. We just
don't say this, but in the case of gravity, what are the states that are in the BRS? Because the simple BRS homology.
These are the states that are left invariant by the free BRS operator. So, for instance, well, the longitudinal component of the transverse component of the graviton.
You don't need to form a curvature, just the gravity.
Well, I mean, the curvature is the local field, because to construct the transverse components, you need to invert. I mean, to do some. To invert by applying some 1/10, I mean, to some Green's functions. So if you limit yourself to the local operators, it would be the tree curvature, or the transverse graviton multiplied by appropriate Laplacian, right, to 1/Laplacian, and all the matter fields, all the fields that transform like tensors. Or, I mean, tensors including scalars, and because all of them transform quadratically under a BRS transformation, so under the free BRS, they are invariant.
But don't they need to be scalars, at least under the special rotation?
Let's see, for when you take a field, a vector field, right? Transformation will have, say, a C mu, well, the mu, and then there will be a term where the H mu index is contracted, right? And there is some derivative acting on C. But both of them are quadratic, right? So this level, all is fine, right? They are all physical. Exactly like in QED, right? When you take the Dirac field and you do the BRS transformation, this is, say, I times charge times psi, and this is equal to 0 at quadratic order, in the linear order, so for the quadratic BRS charge. So you see, it's very easy to construct a very rich homology and then obtain the other one that is non-local. So here maybe I should conclude with some final remarks. So what happens when the Cauchy surface is closed? Well, we don't.
Why is that zero? It's just a stupid question. Why is it?
You mean, oh, because you see, this is a quadratic operator, but in the BRS, the quadratic Q0 transforms linearly. So,
I don't understand.
so
Why are you saying that zero? Why is that? Why is that closed? Why is it in column?
sorry, I would say is under the D0 homology size is invariant. So if you take Q0, since Q0 does not contain any matter fields, right, and then you can and you can understand because this term has to come from a cubic BRS charge. Now, if the Cauchy surface was closed, and at least for QED, we know how to construct that, and for Yang-Mills theory, then, well, the integral of the divergence of A, because we are working perturbative around the background and around the connection equal to zero, right? This vanishes. So also, we also have another object that vanishes, and is the momentum conjugated to the ghost zero mode, which is the time derivative of the anti-ghost. So these two objects actually do not appear in the BRS, in the free BRS charge. They do not appear in the anti-BRS charge R, so they don't appear in the anti-commutator. So they don't appear in the counting operator S. And then when you construct an omega, right, using our R, S, etc., by doing this operation, right, we get a QB that is independent of the zero modes of this ghost, which means that actually the construction for a closed Cauchy surface, our construction needs some extra constraint that have to be imposed additionally to what we had before. And because the QB that I construct with my Q0 does not contain these two modes, but instead the real QB contains them. And unless this integral vanishes, so this is simply the statement that in a closed, for a closed Cauchy surface, the total charge must vanish. This is an additional requirement. I have to impose it. It doesn't come out of the construction. And of course, if we are able to do this, the construction for gravity on a closed Cauchy surface, we discover that we also need H equal to 0. Now, there are other constructions in the literature. In particular, if the gauge theory is broken, we can dress any local operator with the Goldstone boson G and create a gauge invariant operator. So if we have a field psi that transforms in some tensorial representation of the gauge group, we can multiply by appropriate powers of G or inverse of the Goldstone field G and create an invariant field. This expression actually is much clearer when we look at the abelian case. If we have a broken U1 theory where there is a single Goldstone or Stuckelberg field, call it as you prefer, a field of charge Q is dressed simply by multiplying by e to the minus IQ times the Goldstone. And this is perfectly local, right? Psi is local, psi hat is local. And this is the Goldstone or Stuckelberg field transforms linearly under a gauge transformation. So, of course, this object is invariant. So, but this is another Bragg syndrome. And you can actually, this construction can be extended to massive gravity using the corresponding gravitational Goldstone field. These constructions are rediscovered periodically in the literature, but are very old. I don't know how old is this. I think I went back to Weinberg in the mid-60s, but I don't know if somebody did it even before. The construction for the gravitational field, I think, goes back to the late 50s, to Kuchar. But I mean, every few years, people rediscover that and say, oh, who? I think Kuchar is the name. We have the reference in the paper. It's, of course, it's coached in the language of the 1950s, but basically a Goldstone dressing.
Real question is if there's anyone earlier than Stuckelberg. They give him so much credit.
Well, he has a nice tomb. I don't know if you saw it at the cemetery of the Rhine. No, practically yes, the Stuckelberg mechanism on the tomb. Baron Stuckelberg. So now let's. What I wanted to point out is that actually this Goldstone construction is a special case of our construction. In fact, it's clearly seen for the abelian case because it's very simple. Here, I can also split my total BRS charge into free and interacting, but in a different way than before. I take for the free charge just a BRS charge that acts on the Stuckelberg and on the A0 ghost, nothing else. So in particular, I call interacting Q everything that includes not only matter, but also the longitudinal modes of the electric field. So this is a different split. You see, before this piece over here sat in Q0. Here instead, no, I just take for Q0 a charge attacks on the Stuckelberg. The conjugate charge in this case is local. You don't need this strange phi and Green's function. It's this one. You can commute and get, well, you can construct the charge, solve our equations, etc. But in this case, the Q0 and Q1 are so simple that you can immediately write down the intertwiner. You don't even need to think about it. The intertwiner is just this one. It's the Stuckelberg field multiplied by the Gauss law constraint, basically. And so now when you apply this object to our field psi Q, you get precisely the Goldstone dressing. So in this case, all these constructions that existed in the literature and that apply to the case that the symmetry is broken are actually contained in our construction. The case. And in fact, even the Goldstone dressing in a spontaneously broken abelian gauge theory and also non-abelian gauge theory and in massive gravity can be treated in an analogous fashion. So far, we have seen explicitly that if we have a neutral Higgs, we can actually, with some work, arrive at the split of Q0 and Q1 and define something that is the analog of the Goldstone dressing, but now even in the presence of the neutral Higgs. You know, the problem with the neutral Higgs is that if you take this as Q0, the interacting part will also contain terms that have charge 0, so our construction doesn't work. We have to play around and do a canonical transformation to eliminate some offending terms in Q0. But here I think that it's very nice to see that you have this explicit construction. To come back to your question, if you write, in the case of QED, actually omega is also very easy to construct. And basically it has this form, except that instead of phi, here you have capital phi. You know, so the Green's function of the Laplacian times the divergence of the vector potential. And when you commute omega with a charge field, you get exactly Dirac's dressing. So that was our hint. We knew one case in which actually our construction worked because it gave the same result as Dirac's. Okay, so I think that this is a good time to end. And then we'll end, you know, like in Mahler's 10th Symphony and in Bruckner's Night, and we'll end on a downbeat. I talk about states and what we can say about states. So you could formally define physical states in terms of states closed under the free BRS, right? So you could take a field that is a psi 0, a state that is closed and not exact under Q0, and then dress it with omega Dagger. Then this dressed state, at this point not operator, is closed under the complete, the full BRS cohomology. And if psi 0 is not an exact state, then the dressed psi 0 is not exact under Q, the complete Q. So in principle, we have this. And the point is that there are so many states that are in the free BRS cohomology. You can take you have a free theory, right? We're working with free. Take the Fock vacuum and apply transverse gauge fields or matter fields to the vacuum, to the Fock vacuum. and everything, all these states are closed under Q0. So it seems that it's very easy to construct a homology. Now, the construction that I explained is only formal because, in fact, there is no reason to expect that omega actually exists as a well-defined unitary operator on the free field Fock space. So far, what I needed was an automorphism of the algebras. If I want to construct a state, I need omega to be a unitary operator. And as you know, when you construct the evolution operator in interaction theory, interpreting it as a unitary already in quantum field theory is full of problems. We have Haag's theorem and whatnot. So this requires a leap of faith to go from the operator algebra to actually defining a state in this way. Now, the other problem is that if this state was well defined, then the VEVs, any expectation value of the dressed operator will be the same as in the free theory, because then you will dress the operators and you apply them to the dressed state and you get the same as the undressed operator applied to the undressed states. So that maybe is too much of a good thing. Right? You would remove completely the dressing and get an algebra that's too simple. And then there is also a thing that I didn't tell you, and it is that this algebra may not contain, in fact, typically it does not contain all local physical operators. So it is good to have this automorphism, right? For counting reasons, to have some counting of what operators are inside an island or outside. But we have to exercise some cautions in identifying this algebra, where A is the algebra of local operators closed under Q0 as the true one. And so this is the last thing that I tell you. Thank you for your time.
Any questions for Massimo? Any other questions?
Maybe it's a silly question, which is related to what you just said. So about solving the question about the charge operator commuting with the Gauss constraint, if this dressing is unitary and you can reverse it, it shouldn't work, right? Because if it commutes with the dress things, you could just reverse it and find that it also commutes for the undress. So maybe it's silly my question.
Well, so maybe I don't understand your question.
Yes.
So you have an automorphism. So the automorphism is unitary, then the two algebras are unitary equivalent. But I mean, there is nothing wrong with that. You could maybe you may say that that's too much, but that's actually related to the problem that I alluded to here.
Yeah, okay.
There are some operators, some that if you want, you know, in QED, there is nothing wrong with this field, right? It's gauge invariant or the magnetic fields, right? But and it's also, and these fields are also gauge invariant under the quadratic Q0. Right? So now you have, if you take, if O is equal to E and you apply your dressing, then you get a non-local field, because you get E and then there is some plus or minus, I don't remember, times the 1 over, what is 1, let's be super explicit. Times the charge density of Y. Right, so which kind of reverse the story, but the problem again is that you start with the local algebra and you do dressing. It does great things for the charge fields because they are not expected to be local, but there are some neutral fields that are local in the Q0 homology that become non-local. Now, of course, you could start with non-local fields in the Q0 homology and engineer them such that they become local afterwards. But that at least shows you that maybe the complete algebra, the complete QB algebra may be more complicated. But what I think, though, is that we can still use this procedure in a sense to do counting of, say, a rough counting of the dimension of a Hilbert state inside a region versus the one outside.
Eu sou not.
Massimo, the most simple-minded thing that someone would do thinking about this problem is say, fix a gauge, fix a physical gauge, like fix Coulomb gauge, right? To choose your spatial surface, fix Coulomb gauge, and define all the things that are at least that are as local as you can. Of course, there are these 1/x - y's around, but that's fine. And okay, if you want to say it in a gauge invariant way, then just undo the gauge transformation that took you to a Coulomb gauge, and you're done, right? So what's being added here compared to that very simple-minded thing?
Well, I mean, you have to tell what are the local operators, even after you fix the gauge.
Well, things that depend on X.
Yeah.
Local things in X, just the most.
So the local gauge invariant, say the gauge invariant operator, forget about.
Fix a gauge. I don't care about gauge invariant. So fix.
But you should, right? Because if you fix a gauge and you apply an operator that does not commute with the constraint, you get out of that gauge. That's the reason. Dirac didn't do a soft gauge fixing. He really did a hard gauge fix. I mean, divergence of A equal to 0 is 0 equal to 0, right? But there, I mean,
Fix the gauge as completely as you can, and then just write things down that look local in that.
yeah, but is this a physical field or is, I don't know, is A0, well, or AI physical, right? So what happens, you still have to impose at least in a Hamiltonian formalism, right, that your states are either, well, in a hard gauge fixing, we would say that satisfy the Gauss law, but in BRS, they are BRS closed. You have to impose, you still have a big a Hilbert space and you want to stay inside it. So fixing a gauge still doesn't define what is the space of operators, right, that are allowed in theory. And many questions of locality. But when you fix a gauge, even a hard gauge fixing,
Yeah, I'm talking about the hard gauge fixing.
Yeah, when you do a hard gauge fixing, if you compute, say, expectation values of non-gauge invariant operators, they are not well defined. I mean, they're not the same as in the true theory. Even classically, right? I mean, you have to do two things. You have to fix a gauge and then write gauge fixed evolution operators, but then you have to choose the initial conditions. But initial conditions
You have to respect the Gauss law. But
They have to obey the Gauss law.
but
Yes.
That's it. You respect the Gauss law, you fix the gauge.
Exactly, but
then.
Science does not respect the Gauss law, right? Whether you gauge fix or not. So is it, what is the object of those? I mean, respecting the Gauss law in the quantum theory means that you are working with operators that commute with the constraints.
One more question. I mean, you're using you're using the RC formalism, but somehow I mean, there is a spatial slice that you're living on, so Lorentz invariance is not so important. It's not why is BRSC useful here? I mean,
Oh,
it's
BRST, it's
for
useful.
dealing-
I think that BRST, the Hamiltonian BRST has been unappreciated because it is because it's the gauge fixing that we do all the time, and it does not impose the Gauss law either, you know, before quantizing, or it does not even impose the Gauss law on physical states. It's the softest possible way to impose a constraint. Again, it allows to do the gauge fixing that actually we do in perturbation theory, that are those that are not armed, but instead are tailored to have a good kinetic term. And, you know, I mean, it's when all the practical calculations in gauge theory never impose the Gauss law on states. I mean, this thing is, maybe it's done in non-perturbative gravity, but it's never done when we actually compute the scattering averages. What we impose is that, size in the cohomology of Q0. So the state is, when you multiply by C and you transform this into a BRS, Q of size and null state. So I wanted to press, again, perturbative, but I still think that it makes sense to relax these constraints and not to gauge fix. Maybe easier to ask questions about, I don't know how to construct actually the norm of the space. So.
Any other questions for Massimo? All right, if not, again, a reminder, we'll take them to dinner at 6. People want to come, let me know. And let's thank Massimo.